Hi everyone. We're gonna try a comet example today, and I have a degree in astronomy, so I'm gonna kind of ad hoc this. I built this model like 10 times today, and I effed up one of these videos already. So here we go. So we're gonna make Halleys Comet, okay? And you're going to adopt your own comet. So we're going to do, this one's, of course, the famous one, right, from Dr. Halley that Isaac Newton used calculus to prove, and that's how he got his stuff funded, right? Okay, anyway, so here we go, and we're going to use Kepler's Law. So Kepler's Law, I don't know where to put notes, so we're just going to type it in here. Kepler's Law states that here let's go get this Kepler's equation. Oh, we want Kepler's equation, not Kepler's law. Here, so it's mean anomaly and eccentric anomaly, and those are the perturbations. So that's like the wobbliness of it. So Kepler's equation states that the mean anomaly of a body is proportional to the perturbation of the eccentricity anomaly. Okay, awesome. So let's go write that down in math. This means that E equals M plus E times the sine of E, where E is your eccentricity anomaly, and I'll tell you what all this is in a second. M is your mean anomaly, which is mean is average, right? So it's going to be based on an average, and you're going to take 2 pi times the component of the circle that you've covered over time, basically. And then little e is eccentricity. Okay. And that one is eccentricity here. E equals 1 is a line. E equals 0 is a circle, right? So it's usually between 0 and 1. It could be 0 and equal to... so if it's 0, it's a perfect circle. If it's 1, it's a line. Then we don't really use it. So I don't really go up that high. So so some of them are going to have high eccentricity. Some of them are going to have very low. So and with a comet, you're going to have higher eccentricity. Like the Earth is almost a 0. But I mean, we're going to start heading this direction for a little bit of interest. Also, the semi-major axis of the ellipse is proportional to the period through and here, let's say, and if A is in astronomical units, distance from Earth to Sun, right? That's 1 AU. Okay. And period is in years. Then then we can actually calculate this as A cubed equals T squared, okay? And we're gonna go use that here. So so that means we need very little information to actually model this whole thing. So really all we need given is the period, right? So we know the period of Halley's Comet, which is 76. So this is going to be the period in years. Okay, and we need to know the eccentricity of Haley's Comet. I believe it's 0.967. Let's go check. I could cheat. I've already done this once. A different one. This is my other one. What's my eccentricity here? Ah, you don't tell me. You're not helpful. Okay, hold on. Let me go grab it. Okay, we're good. That's correct. Okay, so this is... So this is what you need to go find out. So these are the two that you would find out. And, okay, so once we have that, we're in good shape. So now we can come up, let's compute. Semi-major and semi-minor axes. Okay, so A is going to be T to the 2/3, right? And that's solved from this. Okay, so this is the semi, and we're going to always assume it's sideways, okay? So that it's like an oval that's placed sideways, not up and down, if that makes sense. So semi-major axis in astronomical units, okay? So that means we can compute B. There's an eccentricity formula, which I won't drag you through right now. But it's A times the square root of 1 minus E squared, where E is the eccentricity that we've listed here. So we have a highly eccentric body here. So that's a semi-minor axis in astronomical units. Okay, so that's good. Now we're going to set up, let's go set up empty vectors. So what do we need to have? Well, let's do it like this. We're going to have an E, okay? And I'm going to go from time 0 up to the full year or full period, which was 76. So I'm going to need T plus 1 so I can have that 0 spot, okay? And then by 1. I'm going to use this a lot. So this is going to be my E vector. Okay. And we're going to do a lot of them that look like this. So let's kind of just be lazy here. Okay, M. Going to be the vector of M values, okay? We're going to have an X here, and that's going to be the actual X coordinate because we're going to plot it in 2D. So we're going to go look at the Y value. And then our time vector is just this, so I won't do this. This is a vector of time values, right? So that if I want to say, like, if I want to plot them against each other. Okay, and then we're going to initialize these. So let's initialize the vectors. Okay, so like, for example, E1 is going to start with no perturbation. So we're going to start that off at no perturbation. M1 is also going to be set to 0, and we'll set that as we go. X1, we're going to set out at A, I guess. I have no idea. Negative A, so that it's on the back of this whole thing. Y1 is going to set at 0. Okay, it doesn't matter, but I can't start it at 0, 0. Weird stuff could happen. What we're going to do is we're going to drop it out into space, and we're going to let it catch into orbit, and then we're probably going to delete that point. And I'll show you what I mean. Think about if you're just placing something out in orbit near Haley's Comet, and you know it's Haley's Comet, it's going to fall into that orbit anyways, right? So we're kind of lazy there. Okie doke. We're going to claim that works. You ready for this? For, now we're going to start putting this in. For n goes from 1 up to that time period, from the first year to the last year. And we got the 0th year available to us, right? So the next m value, m of n plus 1, okay, which will be 2, right, when we drop into this loop, is going to be 2 times pi. Okay, that's 2 pi, which is your full circle, right? And then n, the current year that it is, divided by the total number of years it takes to get around. So that's like the fraction of the circle that you've covered, right? So that's your next m value. E to the n of n plus 1 is going to be, okay, this is that formula up here, and we're going to turn it, we're going to use this as an Euler's formula that allows us to plug in, okay? So let's actually just go take that, and that's what we're going to use here. So we're using this Euler methodology. It's not exactly Euler's, but you can see how it is. It's the old value plus some perturbation and a function, just like we were doing in an Euler formula. And as long as that worked, okay. We're going to use x equals a cosine theta, y equals b sine theta, except for we're going to allow it to hit the perturbations, okay? So that's here. See this? So you subtract off the eccentricity. It's a cosine b sine, but you subtract off the eccentricity. This is part of Kepler's equation, okay? So we'll put it up here with Kepler's equation. So then x equals a times, and then it's cosine of e minus little e, right? And y equals b times the sine of e. And that's what we're going to do here, okay? So x equals x of n plus 1 equals, and then it's going to be a times the cosine of e sub n, right? Oh, a times cosine of e sub n minus e. Nope. I don't want that inside of the cosine. There you go. Minus e. Okay. And y is going to look somewhat similar, but a little bit simpler. It's just the b times the sine of e. Okay, so that's accounted for the perturbations and the eccentricity. And you'll notice how much it looks like our Euler's form that we've just done. And so now off of this, theoretically, we should be able to plot. Let's just go try a very basic plot of x versus y in a bunch of, let's say, red circles, so we can see where it's been over time, because with a line you'll just see the circle carved out. Okay. Comet example B. I've made way too many of these today. Oh, we have to use the current value of m. This is really important. All right, it looks like a circle, but it's not. Look at my bounds. So we're going to fix that. And you'll notice that I've got this random spot hanging out that shouldn't be, right? This thing's actually... okay, let's see what we can do here. So, x lim... So the limit on the x value, let's say... Oh, and I don't want to display all the points. Hold on. You saw that weird point there? That's our first guess, okay? So we're going to go from 2 up to all of them, the rest of them. Does that make sense? So that we get rid of that initial guess, because after that we got sucked into orbit, and then we don't look so foolish. Okay. You know, because we were guessing. We don't know this. Let's just put us at a negative 30 to 30. Our semi-major axis is 17. Times 2 would be 34, 35, 36. Let's do it like that, okay? And then, and let's copy this and do the same thing for the y limits on the graph. And there you go. Now you can see what we look like, right? So, so as we come by, we're slinging around here, and that's what our orbit's going to look like over time. As we get closer to the sun, we should go a little bit faster, and we don't have all of that modeled yet. But this will actually give us a pretty good graph of what we look like, and you should be able to like plot time versus x and time versus y. Let's get rid of these. Okay, and we should see that we're like a screwed up sine wave, and then t versus x should look somewhat similar, kind of the cosine version of it. And you can plot x versus y like this. Okay, and now you can see like what's the closest. Okay, the sun is at 0, 0, and you see this gap right here. You're speeding right there. Okay, so you got slung right there. We're at 0, 0, and so actually as we start to look at this, you can see that it slings way out, but near the sun, it actually is right. So the sun's at one focus here, and we're centered at 0. So what happens if we don't use this? It really doesn't change much. It just centers us so that the 0, 0 is at the center of the ellipse instead of off center where the sun is, if that makes sense. So so it's a little bit better modeled if we include that offset to account for where we are. Okay, and so this is pretty cool. This is going to be our model, and what I want you to do is go adopt one, and you can put an X label and a Y label, right? Distance in X, okay, and then you can do the same thing for Y, right? You can put a title on it, okay. So let's put the path of Halleys Comet on here. And now when we run this, I've got a really pretty looking graph that really is pretty accurate, and it shows where we are. Okay. And so what I want you to do is adopt a comet. Have fun.